computer. So welcome to this talk. Thank you for your presence here. Thank you, Christina, for your presentation. I'm going to present my talk. I'm going to share. I'm going to share this talk. Yes, okay. Okay, well. Oh, perfect. Okay. Good morning to everyone. It's for me a pleasure to be here to show you this small results that I have developed in my last time. In particular, it's related, as you can see, with the TXRF application to a complex matrix, a soil, siliceous soil with a high content of metals, by three different analytical approximations, which confer to the TXRF a very important power, analytical power, and overall versatility to analyze quantitatively complex matrix, complex problems. This works into the framework of the proficiency tests made by the International Atomic Energy Agency, exercise number 21, where one of the matrices evaluated was this material, siliceous soil. And you can see that the participation in this proficiency test was very, very high. 98% laboratories around the world that with a generation of data of 2,259 results for 69 elements of this matrix. It's a very, very an important quantity of results which confer a robust statistical validity to the trained data. You can obtain information about this proficiency test in the page web of the International Atomic Energy Agency. Okay, once we characterize this matrix, we have made three approximations to its quantification. Once by using the suspension-assisted methodology, or by using the microwave methodology, and the open vessel acid digestion methodology. These methodologies you can see here. This is an image, a static image of the suspension assisted protocol used for HASI in the analysis of this matrix, where the more important it's the concentration. It's around of 2000 ppm a sample, and the deposited mass is around 10 micrograms, no more. These quantities were enough. In the case of microwave, you can see the process is practically the same. The difference is in the acid attack, acid dissolve, okay, at very high pressure and very high temperature. In this case, the final sample deposition was around 15 micrograms. It's important. In the case of the open vessel, we use this Savage's plate, vessel of Teflon, of PTF, polytetrafluor or ethylene, by use fluoric acid, trying to minimize or dissolve the aluminosilicate present in this sample. Okay, by this way we obtain in the same way around 15 micrograms of sample over or reflector. Thinking in the uncertainties evaluation, for the suspension-assisted microwave and open vessel, we have evaluated 3 parallel analyses and evaluate the results to estimate the expanded uncertainty for a 2 sigma level, that is 95% of success probability. But I know that statistical order, only 3, is not the best, but you know that the limitations are present in all sides, in my home too. Okay, the rawness uncertainty was evaluated in the same way, but in this case, taking one of the depositions and analyzing at 3 different relative position of the X-ray source with respect to the deposition. Okay, you can see. And the instrumental uncertainty was evaluated in the same way, but taking one of the deposition and evaluating the same sample support, the same deposition, and always the same relative position between the deposition and the X-ray source. Okay, in this way we evaluate the instrumental uncertainty. Okay, with respect to the particle size distribution, it's very important for the suspension-assisted analysis. You can see that the blue line and blue circles show the distribution obtained by the original Siliceous sample obtained by received that is to the lab. In this condition, for TXRF, this is not the best evaluation. You can see here particles so big, 400 micrometers, are agglomeration of particles or unique particles very big. This is not, and the average size are very big. So after ringing with a mechanical system that you can see here, we can obtain this suspension, which is really one of the samples suspension. And you can see how we have modulated, how we have moved the sample distribution to values more reasonable, centered in this case with median values around 5 micrometers. But is this right? Okay, really, no. No. Even working in this condition is not a good approximation if we take in consideration, we remember the classic work and reference work of Krokenkamper and Alice Bombolen that you can see, where they define the critical thickness and critical deposition mass or sample reflector in different matrices. If we consider the mineral powder matrix, which is in agreement with the sample, you can see that for thickness, the maximum thickness should be 50 nanometers. But we had obtained an average value of 5 micrometers. There is 2 orders of magnitude of difference. This is very big. So this condition is not implicit, but if we consider the deposited mass, yes, okay, we are around 5 micrograms for the deposited mass, and as if you remember, the deposited mass in this case was of 10 micrograms. Okay, this is in the order, but there is not that 100 factor between for the thickness. So this implies that here there is a question that is not solved, because in this condition analytical results are correct. But then this limit, why not work properly? Okay, even today, I won't say that even today, these questions as simple but simultaneously complex that are not well understood yet. And okay, okay. I want to present only the image of the soil, siliceous soil, from the point of view of the TXRF spectrometer. And here we have the first analytical results. The first analytical results. Okay, here you can see the nominal values and the detection limit. With respect to the nominal values, it's important to see the elemental range. It varies from 19 for the microwaves, you can see, where elements as silicon, sulfur, and chlorine were not analyzed. Silicon, because we are using quartz reflectors, sample support, and sulfur and chlorine because in the acid digestion process, volatiles, okay, in form of gas, really. The best, surprisingly, the best is the suspension-assisted method using methacrylate, because this allows the analysis of silicon, quantitative analysis of the silicon, and also the quantitative analysis of halogen samples, and this is very interesting, of course. But all have a price, and the price is, in this case, the detection limit. You can see that if we use quartz in all this method, we use quartz, the minimum detection limit are achieved, for example, for selenium, rubidium, it's around 1 ppm, but in the case of methacrylate, okay, okay, in this order, it's very big, the difference, okay, and this is the price. All is not possible to have. With respect to the uncertainty, if we compare the suspension-assisted over quartz and over methacrylate, for me has been a surprise to obtain that the best methodological uncertainty was achieved for the methacrylate case. You can see 8.5 with respect to 14 for quartz. Why is this? It's really strange. No, it's not so strange if we analyze the microscopical distributions of the particles over quartz and over methacrylate. You can see if we evaluate the microscopical level, that in quartz there is cluster with different size of elements on theta. Okay, this generate the difference of intensity variation, which generate a high reproducibility for each one, for all the elements, as you can see. But in the case of the methacrylate, you see it's very much homogeneous. It's more smooth, so there is no so big variation for each one of the sample, and then the variability is lower. You can see the results. In the case of microwave and in the case of the open vessel, really are very good result, splendid result. 4.1 for a standard uncertainty of a methodological uncertainty. It's a very, very low, which is a very, very interesting results. And why these results? In this case, the reason probably is related with the symmetry of the depositions. Okay, because the symmetry of the deposition you can see practically circular for all the sample analyzed imply that the variability for each one of them was practically zero. And so here we can see the uncertainty is practically very, very low, no? You know. Okay, if the recoveries, the best recoveries are achieved by the acid digestion, microwave, and open vessel with 15 elements with respect to 19 evaluate. In the case of suspension assisted using methacrylate, okay, we have a chain 13. It's not a very bad result to obtain for correct evaluate data. It's in the order, really, it's in the order. And the correlations of the data for each one of the methods with respect to the consensus values obtained in the proficiency test, number 21. Okay, you can see for the suspension assisted in quartz, the correlation is very, very good in all the case. It's very, very good. 2 or 3 nines of correlation in square R. It's very high, but the slope is not so interesting. The 4 is for suspension assisted over quartz with a slope of only 0.7. After we have similar correlation obtained for suspension assisted over methacrylate and microwave of around 0.85, sorry. And finally, the very good slope obtained for open vessel with a value of 0.93, which was obtained eliminating the, you can see the value of aluminum, because here the recuperation for aluminum was very, very poor. And finally, only say that with all the previous data, I am working to obtain additional data, in particular study the behavior of the detection limit with respect to energy and with respect to time. Only an observation. You can see that we have modeled the detection limit with respect to energy as the factor inverse of the exponential factor, and the time as the Wall-Now relation as 1 inverse of the root square time. Oh, okay, so additional work there is from here, because what is the difference between quartz and methacrylate depositions? There is different in the detection limits, sure, but in the behavior? Next question. Okay, thank you very much.